Hello everyone, we're presenting SOAR, Swarm Operations and Autonomous Rescue. This is our midterm demo, presented by Group 22. Our project is a multidisciplinary team comprised of electrical, computer, mechanical, and aerospace engineers. The ECE team consists of myself, Kate Archibald, Ethan Fleur, and Abdul Memon. The MAE team consists of Nawaf Al-Judaibi, Badir Binafif, and Colin Summer.
Hello, I will be talking about the engineering specification. Firstly, we present the specification for our thermal and standard cameras. We have configured these cameras with a focus on size, weight, resolution, and frames per second to optimize both performance and functionality. Let's head over for the engineering specification that will be demonstrated in the demo for the ACE team, starting with the communication specification. The drone updates global positioning system data at a rate of 10 to 20 Hz. The communication range can extend over 1 kilometer. The GPS system update data at a rate of 10 to 20 Hz, offering a high precision of plus or minus 0.02 degree in latitude and longitude. This accuracy is vital for precise location tracking over a communication range that extend over 1 kilometer. Additionally, an essential component is obstacle detection, which provides a 360-degree horizontal field of view. It can effectively detect obstacles from up to 12 meters away with a 90% accuracy. Lastly, the drone is equipped with a highly precise compass, which is crucial for maintaining the correct heading during flight operations. The compass accuracy of plus or minus 5 degrees ensures that the drone can navigate effectively through complex environments. Continuing with engineering specifications with further details about the battery, motors, and performance matrix of our project. The drone is powered by a battery that supports a current draw ranging from 54 to 77 amps with a minimum voltage input of approximately 22 volts, which will allow for a flight time of 13 minutes. Driving our drone propulsions are the motors operating at approximately 400 kV. These motors deliver a thrust of about 2.5 kilograms, ensuring a powerful lift. Even in the face of technical issues, these motors have consistently demonstrated their ability to lift the drone. Continuing with the MAE engineering specification for performance, our drone features a frame size of 700 millimeter. A larger frame can support heavier payloads. The increased size can also accommodate a larger propellers, which can enhance the efficiency and control. The drone can support a maximum takeoff weight of 3.2 kilograms, and also it can achieve a hover time of about 11 minutes and offers the specific thrust of 7.47 gram per watt. The specific thrust is a measure of the efficiency of a drone's propulsion system, specifically how much thrust is generated for each watt of power consumed by the motors. Furthermore, the drone design focuses on being lightweight, weighing less than 3 kilograms, which enhance its attitude capability. It can operate between 10 meters to 20 meters above the ground, and also having a thrust-to-weight ratio of 2 to 1 is essential for flight dynamics and performance. The 2 to 1 ratio ensures that our drone has the thrust necessary to overcome gravitational forces with a significant margin. This is critical not only for basic lifts, but also for ensuring that the drone can maintain attitude and stability in the presence of variable aerodynamic loads.
Thal payload has arms that are secured with foldable joints. It also has carbon fiber plates on the arms that are made to mount the motors. The plates are made from quarter-inch MDF wood, and it has holes for zip ties and wiring. The carbon fiber rods and plastic elbow joints are going to make up the legs, and they're also padded with soft material at the bottom. The propeller is attached by a bracket and two hex screws that go directly into the motor. The motor is held underneath the plate with 4 screws underneath. Propellers are oriented based on counterclockwise or clockwise rotation. Wires are then twisted down each arm and zip tied to fully secure. Carbon fiber arms are fastened by circular brackets within the square here. The pixel hook is going to be in the center, and it's going to be secured with an adhesive backing. We have a 4-to-1 ESC, and each motor is going to connect to it via ground power and signal. It's going to be fastened metal screws with nylon spacers and washers. Transceiver mounted on the side connects to the flight controller, fastened with metal screws, nylon spacers, and nylon washers as well. Antenna is fastened to the transceiver and is free to move in 2 degrees of freedom, meaning 2 angles it can take. Power is supplied to the ESC and flight computer using a split connection from the battery.
This test was the first test we had. We attempted a flight with 2 batteries, but things actually didn't go as planned. So, as we can see right after takeoff, we noticed instability as the drone had unexpected behavior, which was flipping, likely due to improper ESC and FC calibration, or heavyweight due to having 2 batteries. In this test, we took off 1 battery and we really thought we were into something after adjusting the battery, expecting at least some improvement. But as we can see, the moment we tried to take off, the drone completely flipped into its back right away. It was clear that the issue wasn't just weight distribution, the motors were not behaving as they should, and the drone had no real stability. So later we realized that the ESC and flight controller were not properly calibrated, meaning the drone wasn't receiving signals correctly. This time in this test we finally saw some progress. The drone actually lifted off and stayed in the air for about 2 seconds, which was a big deal. It meant that our thrust to weight ratio was good and the drone had enough power to fly. But then it crashed again. So after reviewing the data, we noticed that one of the motors was lagging behind the others, which caused basically an imbalance in thrust, and this mismatch led to instability. During our flight tests, we tackled issues with weight distribution, ESC, flight controller calibration, and Pixhawk software. As a result of multiple flight tests, we thought it was a motor issue at the beginning, but after swapping a fast and a slow motor, we saw that the fast one became slow. Rolling that out, then we reconfigured the motor directions in autopilot, making clockwise motors counterclockwise and vice versa. Yet, the counterclockwise motors were still lagging, ruling out an ESC issue. This confirmed that the problem basically is software related. So our next step is to flash an older Pixhawk firmware and fully reconfigure everything.
GPS testing. The GPS was tested through Mission Planner and was compared to an iPhone compass as well as Google Maps. It's important to note that 1 degree of latitude equals 69 miles, and 1 degree of longitude is approximately 60 miles at 28 degrees north, which is our distance from the equator. Because one would have to travel a considerable distance to achieve a small change in degree, only 3 tests were performed to minimize inconvenience to the team. Test 1 and Test 2 were performed at the UCF campus and the Valencia College West campus, respectively. The results, as well as the iPhone compass data, are displayed. Here we can see that Mission Planner represents longitude and latitude in decimal format, while the iPhone represents them in minutes and seconds format. This does not raise concern, as there is an easy formula to convert minutes and seconds to decimals, which will be discussed shortly. Finally, Test 3 was performed in Titusville using Google Maps. That data is displayed here as well. Here is a table displaying all of our results. We can note that for all 3 tests, they are within our specification of 0.02 degree accuracy for longitude and latitude. Below is a formula used to convert. You take the number of minutes divided by 60, adding it to the number of seconds divided by 3600. This equation was used for all of the iPhone compass values. At the present time, we are unsure if Mission Planner can represent longitude and latitude with more decimals, but we can conclude that it is properly rounding in its display. One issue we ran into was getting our GPS to communicate on our PCB using I2C. We decided the best course of action would be to use a breakout board instead. This will allow us to easily adjust the protocol to UART and allow for us to have maneuverability of the component, being able to implement a different placement of the GPS if we desire. The breakout board proved to be a success, achieving the high accuracy that we had specified.
We're using a LiDAR sensor to implement object avoidance in ArduPilot. This data is converted into 8 conic sections, which are then used to check a drone's proximity to an object. To test the LiDAR, we connected it to the manufacturer software, SlamTech RoboStudio, which is running on a laptop. We then set the LiDAR on the ground and put markers at 10 feet, 20 feet, 30 feet, and 40 feet. These markers correspond to 3 meters, 6 meters, 9 meters, and 12 meters. Beyond this, any detection would be considered extraneous, as our LiDAR is only rated to detect up to 12 meters. To detect our angle and see which dot we're actually measuring, we had somebody walk along our line of points, and we found that it was within the 67 to 70 degree heading. We then had an object placed at each of the markers to test our LiDAR's accuracy at the 3-meter separations. As for results, when we converted our feet measurements to millimeters, we found that our maximum error was 30 millimeters. This error could be due to human error in measurements or in placement of the object. In addition, variance in the angle could be due to, again, human error in actually placing the box. Our test was a success because ArduPilot flags objects at least 600 millimeters away, meaning that our 30 millimeter precision is absolutely fine for our LiDAR sensor.
The compass was tested using an iPhone compass and comparing the value with what was measured and displayed through Mission Planner. From the test results, it can be seen that it is accurate the majority of the time, only struggling with the northern direction, being off 20 to 40 degrees. The compass is important for the overall system as it provides a heading for the drone and gives the ground team an idea of where the drone is flying towards. This allows the team to confirm that the drone is flying towards the right coordinates as determined by the planned mission to locate potential targets for search and rescue. In the testing recording, the problem with the northern direction can be seen, being off 20 or so degrees. The phone is rotated along with the compass, which is live updated on Mission Planner, enabling the ground team to see data in real time. Although the heading from the compass alone isn't as accurate as desired, its use alongside the gyroscope and GPS is used inside ArduPilot to provide a much more accurate measurement of the drone's heading. For the IMU roll testing results, the output from the custom flight computer was compared to a COTS flight computer and using the output from the ArduPilot ground software, Mission Planner. For each of the measurements, the roll was slightly off, most likely caused by rotating them by hand, as well as the need for additional calibration of the custom flight computer. However, for each of the measured rotations, it was within our engineering specification. The accelerometer is used to calculate the roll angle, using the acceleration measured in the X, Y, and Z directions. The equation is shown here. Additionally, the gyroscope data is employed by the ArduPilot software to compensate for errors and measurements caused by movement, providing a more accurate reading of the roll and pitch angle. The pitch was measured in a similar way, comparing the output on Mission Planner from the Pixhawk with the measurements seen for ours. Pitch was slightly off, most likely for the same reason, caused by having to rotate by hand. However, further calibration will be employed to ensure an accurate reading of the pitch angle as well. The roll and pitch angles are an important facet of our system, as they indicate the direction of the drone rotationally with reference to the ground. This is important when receiving pictures from the drone, as the angular heading can be used to gain a perspective of the current environment. Additionally, each is used for stabilization of the drone, being used to feed into the control loop for the motors for compensation, allowing for autonomous flight. For our video demonstration of the Pixhawk and the Cube Black, two computers running Mission Planner were used to display the orientation of each, allowing for comparison. Each were rotated next to each other, ensuring the correct heading and rate of rotation. Along with the pitch angle, Mission Planner also displays the heading in a heads-up display, allowing for a visualization of the angle of the drone on the ground during flight. Both the roll and pitch angle can be seen as well. This is the board layout diagram of our flight computer used on SOAR. The IMU, altimeter, and MCU are directly integrated, along with the 3.3 volt and 5 volt regulators. Breakouts for the GPS, LiDAR, 915 MHz transceiver, radar, and ESC are located on the edges of the board. Additionally, diagnostic LEDs were added for use during testing and to indicate the MCU was running. The board is 4 layers, allowing for solid ground and voltage references for each row voltage. An ST-Link is used to program the MCU. Resistors were added for each digital connection for better impedance matching, as well as help during debugging.
ArduPilot is our choice of autonomous flight software. It handles both our sensor and our motor implementation, as well as our interface with the ground station. This interfacing between sensors is handled by the GPOS hardware abstraction layer. Altitude measurement is done primarily by the position data from the GPS, which is then combined with our data from the altimeter and our IMU measurements as well. This is also supplemented with our downward-facing radar at lower altitudes. Our heading, orientation, and speed data are implemented by combining input from both the GPS and the IMU. Object avoidance is handled with the LiDAR sensor, which converts its data points into 8 conic sections, which are then used to check the drone's proximity to an object. We use our radar as a rangefinder sensor, which is used for object detection primarily, as well as potential low-altitude sensing. The Mavlink protocol is used to interface from the drone and the ground station. Mavlink is capable of sending commands to the drone from the ground station and capable of sending sensor and telemetry data from the drone, including image data. Our ground station of choice is Mission Planner, which is also part of the ArduPilot environment. Mission Planner is used to as well to configure the data on the flight controller for any tuning that we need for a flight.
As of right now, we have multiple problems that we are working on. This includes the ArduPilot software restricting flight, as it is currently decreasing the thrust of counterclockwise motors while having the clockwise motors at the right thrust level. Our plan to solve this is to reflash with an older, more stable version of ArduPilot to help mitigate the impact of potential bugs, as well as reconfigure the motors. Another problem is establishing mesh network functionality. Our current plan is to configure the radio modules for multi-node functionality through the RFD tools suite. Another problem is that while testing for the midterm demo, the LiDAR sensor connector to the PIC sock became non-functional. This is a simple problem and only requires making another connector to fix. For the radar module, we discovered that it required low script knowledge to write the new driver, as we previously only thought that we needed to write with the GBOS HAL. Although it is possible to work on, we decided for the interest of time to go ahead and select the new radar module for easier software implementation. The last problem is the major problem that we are dealing with. As of right now, since we are unable to fly manually with the drone, we have been unable to test autonomous flight. Our approach to this will be using defined missions and Mission Planner to test flying point to point once we find that we can fly manually.